Hey there, Mohit, this side. This is the continuation of the series that uh, for square roots that we were talking about. In the previous video, I have talked about the prime factorization method. If you haven't seen that yet, you can go just check it out. Today, we are going to talk about the division method. Okay. So, division method is like tracking. It technically demands some high level of attention. Maybe you will have to remember few of the things, but it is actually perfect. This method is reliable for finding out the square roots of both perfect and imperfect squares and can give any required degree of precision. Means if you want the square root to, let's say, 4 decimal place values precisely, division method is the only way you can approach, and probably it is one of the best method in my opinion. Also, one more thing you need to notice here, that it is popularly known as log division method. Today we are going to talk about these three examples. One having 5 digit, so all 5 of the digits you will get to know how to deal when there is a lengthy example, long calculations we have to deal with. And then we will talk about 101. Sometimes the number can get tricky even if they are not large numbers, just like we will notice it in the case of 101. And then we'll talk about 2.4025, not really a whole number, a decimal number. How to deal with those. I have also seen the teachers explaining this method with various kind of examples, but so far I have not came across any of the examples wherein the decimal numbers are explained. But in reality, we can use the long division method for any kind of numbers, all kind of numbers. Well, we are not talking about the irrational numbers and all that, imaginary numbers. And we are leaving all those things, but we are talking about the decimal numbers, whole numbers. You can take any kind of numbers and then you can apply division method. Let's talk about 73,441 or 73441. So we'll just, as the name suggests, it is long division method. We are going to do what we would do for division, right? And then let's take the number, the similar things like we would do in division. Let's come to the step 1. Group the digits of the numbers in pairs. We have to make pairs. Okay. So starting from the right to left, we may say, because we will start with the smallest place value and we'll move to the largest one. In the case of no decimal place values, right? We are talking about only whole numbers. If there are only whole number present, you start from the smallest place value, move to the greatest place value and make the pairs. What I'm talking about? Just like this. 4, 1, first pair. 3, 4, second pair. And 7, the third pair. Here we can notice that 7 can be considered as 0, 7. Okay, because that's how you may write the number if you really need pair. Because at the end, you may add another 0. That doesn't make any change in the value. Also, we can notice that it is still a 5-digit number. Putting a 0 just next to 7 doesn't make any 6-digit number. It still remains 5-digit number. Step 2. Find the largest perfect square number that is less than or equal to the first group from left, obviously, right? Starting with the largest place value, I may say. Okay. Start with the largest place value. Which one do you think is the largest place value over here? It is 7. So we will talk about 7. Okay. Let's do it. We notice that 7 is here. I wanted to tell you that you need to remember, or at least I'm pretty sure you all know about the squares of 1 to 10, right? So you need to know squares of 1 to 10 numbers. Practically, you will never use 10, but I still added it. So let's talk about the number 7. Where do you think the number 7 lies? We have to eliminate all the numbers which are greater than the given number. If they are equal, we can take that. So we have to find out the numbers either equal or less than the number. Okay. So we may notice that 9 is the greater number, which implies that all the following numbers will obviously be eliminated. That leaves us with the number 4. Why not 1? Because it is too far away, right? In the smaller numbers, we have two choices, 1 and 4. 4 is the closest to 7. That's why we will take 4. So where we'll take it? We'll take it right next to the 7, just like we are doing the division, right? Now, if we want 4 there, what do we need in those 2 boxes? So that's 2. Yes, you got it right. So 2 times 2 is 4. That's the step 2. We have completed step 2. Fine. Step 3. Subtract the square of the number that you found from the first group, right? We'll subtract it. 7 minus 4, 3. Fairly simple, right? After subtraction, you will get 3. Now let's move on to the next step. Bring down the next pair of digits next to the remainder. That's the new number to divide. Okay. Just like how we are doing division, 34, we bring it down and we have the new number 334 or 334. Let's move to the next step. Add the current quotient with itself. What is the quotient right now? 2. We will have to add 2 with the 2 that we have got as a divisor. It was the first step. Here it is going to remain the same, but you will have to take care of this step. Whenever we are moving to the next example, I'll explain that. Okay. So we will add 2, which is the last quotient, with itself, giving us 2 plus 2, 4. Notice one thing here. Write it as a partial divisor. What does it mean? What do I mean by that? I mean to say that we are not going to leave this 4 where it is. We are going to shift it 1 place value. Means we'll move it forward, or in just mathematical language, if we may say, we'll append it, right? We'll append a blank space there. Technically, we will append 0, but we are not going into the details right now. Now see, find the next question. We are trying to find out the next quotient. Okay, but there is a condition for that. What is the condition? The only condition is that the number in the yellow box should be the same number. Can you notice 2 of the numbers, right? We need the same number over there. So it might be 0. So, right? So if we talk about all the possibilities, it leaves us with 10 possibilities. What are those 10 possibilities? As I told you already, right? So we may start with 0, 40 times 0. That is the first possibility. Then we can talk about 41 times 1, right? That's the second possibility. Then we can talk about 42 times 2. Then we can talk about 43 times 3. Then we can talk about 44 times 4. Then we can talk about 45 times 5. And then we can talk about, all the upcoming 46 by 6, 47 by 7, 48 times 8, 49 times 9. These are the 10 possibilities we are left with. Now, just like how we did with 7, to figure out that whichever is the smaller number that is closest to 7, which was 4. We are going to do the same exercise here. And we found these answers. Now, let's talk about it. Which one do you think is the closest one and yet smaller? It is 47 times 7. Okay. So we are going to take one more thing. We are going to take 47 times 7. But see, you may think this is a lengthy, but it is not. Because we don't really need to do it every single time. Why? Because you can observe over here that what we need has the tens place value 4, 1 digit from there. And what we need, 334, 2 digit from there. And you can just estimate it. Like, what would I multiply with 4 to get the answer 33? Actually, you can't, right? But I can get 32. How do I get it? 8. So, the best approach would be that you directly try 8. What I'm trying to tell you is you directly try 48 times 8. That leaves us with 384. Now we know that it is a little bit greater than 334. So that's not required. We may try the smaller number then, right? That is 47 times 7, right? So we try the smaller number, 47 times 7. That's what we concluded from the earlier conclusion out of all those 10 possibilities. So fine, that's it. We put all the numbers where they are needed. 47 times 7. Notice that in both the boxes, 7 has been put and 329 has been put where it needs to be subtracted. We'll subtract 324. Sorry, we'll subtract 329 from 334, leaving us with 5. We'll have the remainder 5. Now see, we have technically completed all the steps, right? Now we just have to repeat from step 4. Okay? Fine. So let's bring down the next pair of digits, and that's the new number to divide, 544. Sorry, 541. Add the current quotient. What was the current quotient? 7. We will add it with 47. 47 plus 7, 54. Attention here, students. Make sure that you do not add 47 with 47. I have observed this many times where students generally tend to add whatever they are left with on the, left side. But we don't do that. 47 plus 47 is not intended. 47 plus 7 is intended. That is why I have written add the current quotient, not the divisor. Okay, because here we are having a divisor in 2-digit quotient. I'm actually using the wrong terminology. We shouldn't call it divisor and quotient because this is not really the exact division. But please note, this is a probable mistake. That's why I'm telling you that 47 plus 7, not 47 plus 47. Okay, good to go. Fine, 54, we'll write it as a partial divisor. And then we will find the next quotient, right? Again, you may observe both the yellow boxes, right? 541 times 1 is 541. See, you need to notice these things, okay? How do you notice it? That you need to 540, you when you try to figure out those 10 possibilities, as I told you, that you take 54 and then you take 2 digits if you are taking from this side, 3 digits you will have to take from that side, right? Sometimes you can get the idea just by looking at the number. 54 you have. 541 times 1 gives you 541. I'm just, trying to explain it because this is the first example. There are so many coming, so we'll practice it. Fine. We have no more pairs to bring down, and we also have got the 0 at the remainder. That means we end it here. There is no need to do anything more than that. Still, we'll add the current quotient with itself, right? So we get 542. Why do we need to do that? For the verification purposes. See, now when we verify, we notice that we have 2 ways to do that actually. We have got the answer 271. This method says that 271 is the square root of the number 73,441. So we can multiply 271 with itself and get the answer. If that answer matches with the question, we can say that this number is correct square root of the given problem. But there is one more way to do it, right? What is the other way? If the number 542, you can observe that the number 542 there should be twice of the number, right? 271 times 2 equals 542. So I'm telling you the same thing, that the number over here at the end, that should be twice the quotient. 271 times 2 is 542. That's it. We have verified. Implies square root of 73,441 equals 271. That's it for the first example. Now we'll be moving a little faster. Okay? Fine. Hold your seat belts. Let's talk about the number 101. We move to the first step. We draw the division box. 101 written as the division. Then step 1, we'll group the digits. We only have 2 pairs over here to make. One having 1, the other one having 01. Then we move to the step 2, largest perfect square number that is less than or equal to the first group. You notice that it is already there. The first group is 1. That itself is the perfect square number, so we write it there. 2 empty boxes. What should I write into those 2 yellow boxes? Obviously number 1, right? Gives us 1 ones are 1. Subtract the square of number you found from the first group. We'll have to subtract 1 minus 1. That gives us 0. And we bring down the next pair with the next step, right? That leaves us with the number 001, or in short, 1, right? So now here is the catch. Add the current quotient with itself. So we'll add 1 plus 1, and that makes us 2, right? And then we'll write it as the partial divisor. And then we will find the next quotient, which will leave us with, remember the only condition that these yellow boxes need to have the same number. Again, leaves us with the 10 possibilities, but we are not going to talk about all those 10 again. We are having 0 this time. 20 times 0 equals 0. Why? Because 1 is not there in all those 10 possibilities. Only 1 we are getting, that is 0. So we get it. Fine. Now we will repeat the steps, bring it down the next digit. See, 101 has, ended in a remainder, with a remainder. We are having the remainder 1. That means the process is not yet ended. Still, we are not getting the remainder 0. And therefore, we cannot end it. We can also say that 10 is not the square root of the 101. But if you are just estimating, you can, write with some of the decimal 10.0 and something. But that is why we have to extend. Whenever you come across this type of numbers, you extend it, because 101 equals 101.00. So we extend it with 2 decimal place values we have added in. That will be a new pair, the next pair of digits whenever you encounter this type of number, because you already don't know that 101 is a perfect square or not. Here, this is the smaller number, you know it, but 73,441, we talked about the earlier number. Was that a perfect square? Did you know it beforehand? No, obviously, right? So we cannot. So if we need, we can add those decimal place values. Okay, that is fine. Gives us 100. That is the next number to divide. Now, 20 plus 0 gives us 20 again. We'll write 20 as the partial divisor. And then we have 10 more possibilities. Again, you think about it. 200 times 0, 201 times 1, 202 times 2, 203 times 3. Right? We find the next digit. We notice that there is no 100. 201 times 1 is 201. So only one possibility we are left with, that is 0. Right? You notice that whenever there is a 0 coming there, it is making our job a little catchy. You need to take care. 200 times 0 is 0. So 100 minus 0 is 100. Now this time we are going to have 4 digits. Can you imagine the number 101 having the calculation including 4-digit numbers? This is why I have taken this number. So we add the pair of zeros as and when needed. I have added one more pair again. This is the reason why we can do this, and this is the reason why I'm calling this method as almost perfect. Okay. Excluding some of the irrational numbers, you can literally deal with every other number and figure out the square root of that number. Considering yourself a calculator, you can do it as precise as you want, as many decimal places as you want. So we bring down the next digit, and that number is whooping 10,000. Add the current quotient with itself, 200 plus 0, 200, and we shift it. That makes it 2000 times 0, or 2001 times 1, 2002 times 2, 2005 times 5, and all those possibilities you can think of. How do we do it? 200 times what number is 1000 is the question. Why did I take 200? Because there are 200 over here. And if I'm taking 3 digits from this side, I'll take 4 digits from this side. If I'm taking 2 digits from this side, 3 digits from that side. Simple. Okay. Don't make it too complicated. If it was 20, I would be taking 3 digits, which was 001, whatever. Okay. 200 times what is 1000? 200 times 5 is 1000, right? So we notice we append 5 with 200, making it 2005 times 5. That gives us 10,025. The number is crossing it a little bit, just by a little sort of number, but it is still not okay. So we will take 2004 times 4. That is the desired outcome we want here. So in the yellow box, can you now decide, or can you guess which number will be there? 4, obviously, right? So we put 4 on in both of those boxes, giving us 8016. We subtract 8016 from 10,000. And from step 4, we can repeat as many times as we want. But we don't repeat. Let me tell you a fact. If the number is not a perfect square, the square root of that number is going to be an irrational number. Meaning that after this decimal, if you continue this process, it is going to repeat many of the number without any pattern, completely, you know, uh, random. This is not going to end. So two decimal place values are considered good enough of an approximation. So we'll leave it here. Square root of 101 is nearly 10.04. We end it here. That's it for the second number. Now we'll move a little quickly because it has been quite a lot. So we'll move on for the next number. Fine. So the next number is 2.4025. Again, we write it as the division. And again, we start doing it with the pairs. But again, we have to group it. And here there is something that you need to take care of. That is the catch over here. So we'll take some of the examples for pairing. How do we pair if there are decimal numbers present? Whenever there is a condition like 12.298, you may want to start pairing like 98 and 22 and 1 and all that, but that is incorrect. Why? Because consider decimal point as an origin. And from that origin, you move in both the sides. Like you are expanding in both the direction, right? So for the whole part, you start from the smallest to biggest place value or smallest to the largest place value. And then for the decimal part of the number, you start with the largest decimal place value and move to the smallest. If there are not enough number of digits that you can pair them, you add a 0 whenever needed. Okay. We'll take one more example. 100.29857. So you may be prompted to start from the left, as I told you earlier, but that was for the whole number part. For the decimal part, we pair the digits like this. Okay. You can observe the correct pairing and incorrect pairing. The incorrect pairing, in the correct pairing, you may also notice that at the end, I have added 0. For the whole part, it is optional, but for the decimal part, it is compulsory. Otherwise, you will just bring down 7. Don't do that. Fine. So that's step 1 completed. Step 2, largest perfect square. We all know that we have to deal with 2, and that is 1. The largest perfect square that is less than or equal to the number, which is 1. So in both the yellow boxes, we'll have 1. Fine, 1 times 1 is 1. Again, we'll subtract. So 2 minus 1 is 1. And then we'll write 1 and we'll bring down the next pair of digits, that is 40, and giving us the number 140, right? Move quick, because now we have already taken enough time. We add the current quotient with itself, and that is 1 plus 1. So we get 2. We now shift it as the partial divisor, and we get 20 times 0, 21 times 1, and all those 10 possibilities. Also remember this condition because it is really, really important. We need the same number in both the boxes. We notice that 25 times 5 is the appropriate choice. You can try that with all those 10 possibilities yourself, right? At least that much you can do. Now we subtract 125. We put 5 in both those places, and then we get 15 out of the subtraction. And then we bring down the next pair of digits, making us the number 1525. Okay. Don't forget to add the quotient, that is 25 plus 5, making it 30 for us. And then we'll write it partial divisor, making it 300 something. Okay. Now, if you notice closely, the number we want ends with 25, right? So by your instincts, you should be knowing that the number we should be trying first should be 5, because that's how the squares are defined, right? So we try 305 times 5 and bingo. 305 times 5 is 1525. We got the number, we got the subtraction, and after the subtraction we are left with 0. No more pairs to bring down, and here we end it. Just imagine a number looking easy, 101, may cause you some trouble. I'm just guessing that it may. Actually, if you are smart enough, this should make sense and it shouldn't cause you trouble anymore. But if it is, you can just estimate it. Over here, you can complete the adding process, 305 times 5, and then you can get 303. If you just ignore the decimal, we have 155. If you double the 155, you get 310. So we verify that, and that gives us the answer of square root of 2.4025 equals 1.55. One we had to estimate because it was an imperfect square, and the one was a perfect square and the other one was a decimal number. So we cannot call it a perfect square, but rational perfect square we can call it. So that's how we do it. That's it for the division method. This video, it took a little bit longer, but that's it. That's it for the division method. I would first like to tell you more about this division method. See, sometimes it happens that, my personal observation and my own philosophy has been that if you understand something really well to the core, if you really get the core idea of that concept, you don't really need to remember so many of things about it. And trust me, after a few years, you will realize that the more you remember, the more you will have trouble. So I would suggest that rather than remembering it just as a abstract information, you get to the very core of the idea. If I'm getting a good response for this one, I'll be coming up with the core idea or the actual logic behind the division method. Okay, that is also very beautiful. And if you're really keen to know mathematics, you will love it. So fine, that's it for the division method today. This was the part 2 of this series. I'll be coming up with the estimation method really soon, which is the part 3. So if you think that I provided some value and, if you think I made a difference, consider subscribing and don't forget to like and share.